Okay, the purpose of this video is going to be just to strengthen our skills on this transformation stuff. We're talking about data that is not in a linear pattern, and we're going to focus on one of two ways to fix that. We're either going to log y, which is exponential, or we're going to log both, and that's called power. So what I'm going to suggest as you watch this is to pause your video and try to answer these 4 questions. Do the linear regression, do an exponential, do a power. Choose which one is best and use that to make a prediction. Okay, so pause, answer those, and then there's not a whole lot to write down just to follow through on the calculator. Do these steps on your calculator. Being able to do these is what I'm going to be testing you on soon. So you need to make sure you know how to do these steps. All right, so hopefully you've paused and tried, so let's go through these answers. First of all, here is my data. And here is my graph. Okay, so this definitely appears to have some curvature to it. I'm going to do linear regression and put the line through. This is just on x and y. I haven't logged anything yet. So I'm going to do stat calc 8. Remember not to use 4, you got to use 8, a plus bx. And I'm going to do this on list 1 and list 2 and comma vars, y vars, function y1. And that's going to put the line through the dots for me. Okay, so you can see the line has showed up in my graph. You can see my correlation, it's 0.959, and my equation would be y equals it's let's see, negative 0.16 plus 0.21x. And the correlation on that straight line value is 0.959. So we've seen some examples like this before where the straight line correlation is pretty good even though the data is obviously nonlinear. So you can't just look at that high correlation and say that a line is a good model, because this is definitely not a linear pattern. Now the point is next to decide, is exponential best or is power best? And what probably will happen a lot of times is that both of them will be very good. It's hard to tell from this small sample which one is best, especially if we don't know the context. If you're talking about a population growth, something like that, it's probably exponential. If you're talking about length versus mass, something in a biology type situation, that lends itself to power. If we don't know any context, we're just going to check and see. So in my lists, I'm going to go ahead and log both. I'm going to do the log of my x's. So go up and highlight L3, and I'm going to do log of L1 to get the log of my x's. And then I'm going to go up in L4 and do the log of list 2. And that'll be my log of y's in list 4. So the next option, or the next question, number 2, is do an exponential model and write the equation. My exponential model is x versus log y. Okay, so first of all, I'm going to graph x versus log y, which is list 1 and list 4. I'm going to go into my scatter plot and graph 1 versus 4. So if I just go to my graph, that's probably, it's going to still show the y that's there from my last linreg. Every time you do linreg, you're going to have to do a new y. But if I do zoom 9, that'll take me to my new dots. Okay, so that's straightened out pretty well, but it looks like it still has a little pattern to it. So let's see when I do linreg. Stat calc 8. This is x, which is list 1, log y, which is list 4, and let's put that into vars, y vars, y1, and do that over. So you can see that, oh yeah, there it is. It appears on my graph. It has added it in to the dots that I had. So in 2, and by the way, I need a y hat there. In number 2, I have log of y hat is equal to negative 1.76 plus 0.599 x. And I had a pretty good correlation as 0.995. Even with this one, though, if you look at it, and a residual plot would show this a little better, we still have some curvature. All right, the residuals that I just made of 1 through 4, let's look at that for a second, because I want to talk about residual plots while we've got a chance. I'm going to go up and do list 5 and program it to be, if I go to second stat, for me it's option 8, residuals. Every time you do linreg, you get a new set of residuals. Now I'm going to graph 1 versus 5. And zoom in on that. Okay, so you can tell this is definitely not linear. The curvature that you can barely see in the scatter plot after I do an exponential is very obvious in this graph. So this is not linear, which means my exponential model isn't really a straight line. It's still got some curve to it. Now it's still pretty good. I mean, the correlation is very high, but let's see if power does any better. Okay, so power is log x versus log y. So that's my list 3 and my list 4. So let's start with a picture. Graph list 3 versus list 4. Always zoom 9. All right, and that one looks like it's got some curvature as well. Let's do the linreg. Stat calc 8, list 3, comma, list 4, and I'm going to put that into y1, and that should add the line. Okay. So a power model gives me log of y hat is equal to negative 1.19 plus 1.98. And now this is times log of x because both were logged in this case. And the correlation that time was 0.98. Okay, so what it boils down to is our exponential did the best, even though exponential, which I've lost my graph of, it showed a little bit of curvature the way this one does, just not quite as much. So if these are our 3 options, either regular straight line, exponential, or power, the exponential is the one that worked the best. And there are other ones, if you want to read through 4.1, which I know you'll do just for fun. There are lots of different ones, but these are the ones that we're going to focus on. So in our case, exponential was best. So let's use the exponential model to predict. Number 4, since exponential was best, we're going to be using 10 to the negative 1.76 plus 0.599x. Remember, you can't just plug in your 2.5, which is our value for x in the question. You can't just put that here because that's log of y versus x. The undoing of the log is the 10 to the. So we need to do, let's see, 10 to the negative 1.76, 0.599 times 2.5. All right. 10 to the power, parentheses, negative 1.76 plus 0.599 times x, and that was our 0.599 times 2.5. And remember, this is a model. This is for prediction, what's going to happen at 2.5. We'll read in the next section about extrapolating and all the cautions you need to take when you do something like this. But this is our best of our 3, our best model. We get 0.546 as our prediction. So if you look at your original data, that should make sense. If we get up to 2.5, 0.546. So let's look at our original data. It's backwards for no particular reason, but the data, you can tell that as we go from down here at 1, we have 0.07, 0.08, 0.1, and then it starts growing a little faster. And if I go back to my original graph of 1 versus 2, That'll probably be a better visual. Zoom 9, always zoom 9. You can see how it's starting to get steeper. So if we went another 0.5, this graph is from basically 1 to 2. So another 0.5 gives those dots time to really climb up this way and get steep. That's how we get all the way up to our final answer, which was 0.546. All right, so that was just one more review that I wanted to make sure. If you did not pause and do those steps, go back and do it. Just make sure. The part I'm going to be testing you on is, can you do this stuff in your calculator? So the calculator work is the material. Make sure you're able to do these things. All right, so if you can do that, you're in pretty good shape. And I will see you at school. Out.